Swayam Prabha. Digital India. Educated India.
So good day to all of you, and welcome back to our lectures on stability of slopes of landfills, which I think we are continuing from the last one or two lectures we have already had. Okay. These are critical issues for landfill design, because I told you that if a landfill is above the ground, the slopes have to be stable, and if we have put some geosynthetics inside the slope, the tendency is for the cover soil to slip off. So we have to be very careful that for 50 to 100 years, this mound that we create, it remains stable. So let's just briefly recap what we did last time. So we said when we are discussing slopes, we have to look at failure along excavated soil slope, which is this one. Then we have to look at failure along the waste slope, which is this one. That is the temporary waste slope. And then we have to look at failure along interfaces in the liner, that means in this and in the cover. And the most critical one was that in the cover, it's going to be long-term stability issues. The slopes that we are preliminary section, the slopes that we use in the preliminary section, typically excavated soil maybe 2:1. We may keep the waste slope 2.5:1. For the liners 3.5:1, and for the covers 4:1. That's the average of these. Now when you do the slope stability analysis, you'll get a more accurate handle as to what slopes you should adopt, and you can fine tune these slopes. And I know everybody wants to make steeper slopes so that you can store more waste. So you do the stability analysis and see what are the actual slopes which emerge, because each site will have a different soil and different climatic conditions, how much rainfall will fall, how much earthquake will be encountered. And we also looked at the fact that if we have a permanent slope, then what kind of acceptable factors of safety do we look for? And if we have a temporary slope, what kind of acceptable factors of safety that we look for? Stability along interfaces is what we started last time, and we said that the moment you put a polymeric material inside, an interface develops, and you have to look at the stability along this. And it is usually treated like an infinite slope problem, because this is a long slope in comparison to the height of the failure. We also said that these interfaces can cause the temporary wastes to become unstable, because the liner may have low shear ring resistance at the base. And this is a typical cover system with all the interfaces. And historically we started by using smooth geomembranes, but soon we found that smooth is bad. So the manufacturers started giving us textured geomembrane. So the deltas went up, the stability is improved. However, the moment the factor of safety would not be met, this weight of the soil would tend to move down, and you would require some kind of a reinforcement to hold the soil. Therefore, there was an attempt that can we reduce the weight on the top. You know, the driving force is what? W sine beta. If I can reduce W, I can reduce the driving force. So the tension which the reinforcement will have to overcome is reduced. So one of the ways of doing it is to replace this sand drainage layer, which is 30 centimeters thick, by a geocomposite which is 5 millimeters thick. So that's a lightweight material. And If it still is not stable, you could introduce a geogrid, that means a reinforcing element which could give you capacity to hold the tension, or which could give you a force in the opposite direction to the driving force, and that could overcome this weight. So these are some of the methods by which we can make slopes to be steeper. And of course, we also talked about the fact that there are suggestions that we can use the geosynthetic clay liner at the bottom to reduce the amount of clay that you need and get more space for storing your waste. We briefly looked at the parameters and we said we should work with residual values. And when we looked at smooth and textured geomembranes and we looked at the sand on top, with smooth we were having 17 to 20 degrees, but with textured we went up to the 5. The critical one was if you have a smooth geomembrane with saturated clay, you would have very low delta angles, but with textured you would get better values. We also looked at, because now you have interfaces, if you look at these interfaces, you will see that it's no longer a sand to geomembrane interface, it is the geotextile to geomembrane interface. So earlier we have said if you place the sand directly, what happens? But if you have a protector in the form of a geotextile, you need this angle, geotextile to geomembrane, and that we can see here, that if I have a smooth geomembrane and I put a non-woven geotextile on top, it will be 7 to 10 degrees. However, if I texture it, it will go to 15 to 18 degrees. So texturing was always better, and we need these delta values for design. Another important issue that I talked to you about was the geosynthetic clay liners, and we remember that these have got bentonite between two geotextiles, and I said these GCLs only work when they are hydrated. That means you have put water on them and the bentonite is swollen and it does not allow any water or air to pass. But hydrated bentonite has very low strength. So when you are going to use a GCL on the slopes, please be aware of this, that earlier, just like we started with smooth geomembranes, we started with unreinforced GCLs. Means they had the sandwich, there was bentonite between the two geotextiles, but the residual strengths were very, very low for hydrated GCLs. Then what they started doing was they started stitching between the two geotextiles. So that meant that when these two want to shear, if there is no stitching, then when they want to shear, the shear plane is through the bentonite. But if there is stitching, then it gives you additional shearing resistance. So reinforced GCLs are better than unreinforced GCLs. They are more expensive, but all manufacturers will tell you that we have these two types of GCLs, and please be very sure that if you are using them on slopes, use the reinforced GCL. The other question which comes out is, if the GCL is just under the geomembrane and it's hydrated, then during hydration the bentonite can extrude from the pores of the geotextile. The question which comes to our mind is, what is the interface shearing angle between the hydrated GCL and the geomembrane? Well, if the geomembrane is rough and the geotextile on top of that has a significant angle with the geomembrane, what normally is observed is internal strength will govern, which is this one. So the interface may not become critical if the internal strength is low. If it is a reinforced GCL, then the interface may become critical, and you have to ask the manufacturer, or you have to perform the laboratory tests where you hydrate the GCL and slip one membrane over the GCL. We also remember we talked about the driving force and the resisting force and the factor of safety being the ratio of the two, and if the driving force is more than the resisting force, we said we can use a reinforcing element which will take some tension. Now please understand, geomembranes can take some tension, but they are not designed to be reinforcement. You remember a geomembrane, if you pull, for it to get its full yield strength, it will have to, how much does it elongate by? When you linearly pull a geomembrane, 50 to 100% is because you said these are flexible materials. When you want reinforcement, you want a more rigid thing. That means soil should not start moving downwards for the full strength of the tensile member to be developed. You want it more to be like the RCC bars that we have in concrete. So, geogrids are the true reinforcing elements. But do remember that geomembranes also have capacity to take tension. Geotextiles have very low capacity, so they can mostly be neglected. So, I am going to use the term T later. This is T, and typically geotextiles you can take very low or neglect unless it is a high strength geotextile. Geomembranes would be one order of magnitude, say 15 kilonewton per meter, and geogrids would be a next order of magnitude, say 50 kilonewtons per meter or 60 kilonewtons per meter. So, geogrids are the true reinforcing elements that you can use. We said that we can do the analysis using the infinite slope method, and the factors of safety would basically be the ratio of the N tan delta is the resisting force and W sin beta is the driving force. N is equal to W cos beta, so it becomes W cos beta tan delta, and the factor of safety became tan delta by tan beta. That means if you have the slope at the angle of the interface shear resistance, then factor of safety will be 1. Say delta is 25 degrees, your slope is also 25 degrees, so tan 25 by tan 25 is 1. You want your slope to have a factor of safety of 1.5, the slope inclination we have to be less than the delta. Otherwise, you will need a reinforcing element to hold the slope in position. So, either you can go for a gentle slope. Should you want to make it steeper, you will need a reinforcing element. And do understand, reinforcing elements are not going to make the slopes very much steeper. Reinforcing elements will change the slope marginally into a more steeper solution. Other than the weight of the soil, there are other factors which cause the factor of safety to go down or go up. So, if you have seepage, then the rainwater tends to travel downwards, so it causes the factor of safety to go down. If you have an earthquake, a horizontal acceleration may emerge, which will cause the factor of safety to go down. If you have a reinforcement, it will give you a T, which will enhance the resisting force, and therefore your factor of safety will go up. So, these are the three major things that you have to take into account. So, let us look at the formulae which emerged from infinite slope analysis for stability of this interface element. All that we are saying is this is the geomembrane, let us say, and I have a sliding mass, and we have said that the driving force the resisting force is and therefore the factor of safety Now what happens if I add seepage or if I add earthquake? So, you have to set up the free body diagrams, and I am not going to get involved in setting that up, but remember seepage force, rainfall, it is stopped here, therefore it begins to go like this, and therefore the seepage force or the drag of the seepage force is downslope. It causes instability. How much instability it will cause? It will depend how much water is inside the system. And the formula that is given to you is, it is the same formula, tan delta by tan beta multiplied by, when seepage is parallel to the slope, to the slope. Factor of safety is still tan delta by tan beta, but it is W effective by W total, or W whatever you want to call it. Just for the purpose of discussion, normally this will not run in the full soil. So it gives you the concept of a submergence ratio. Submergence ratio is equal to, if this is HW and this is H, submergence ratio is HW by H. The lowest value it can have is 0 and the highest value it can have is 1. When it is 0, it becomes the case of dry soil. So what happens to W effective? W effective, when submergence ratio is 0, W effective is equal to W, it crosses out and your factor of safety is tan delta by tan beta, right? When the submergence ratio becomes 1, what happens? Then the W effective becomes gamma submerged into the volume of the soil, and the W total becomes gamma saturated by the volume of the soil. So when SR is 0, it is the factor of safety is the same as this. But when SR is 1.0, then your factor of safety becomes gamma buoyant or gamma submerged divided by gamma total or gamma saturated into so if give me a normal value of gamma saturated. This can be gamma submerged or gamma buoyant, and this can be gamma total or gamma saturated. Shall I write this up here? Because if you can't see it, this is the whole thing is multiplied by tan delta by tan phi, tan beta, sorry. So if you have a normal soil, what is typically the value of gamma saturated? (20 kilonewton per meter cube). So what will be gamma submerged? 10 kilonewton per meter cube. What is, therefore, what happens to the factor of safety? It becomes half of what the factor of safety is for the dry case. So the slope may be stable while it's dry, but it will not be stable when it is raining heavily. So your drainage layer, which we are designing, must be able to capture all the water and take it down without the soil becoming fully saturated. So typically you should be able to work with the submergence ratio of 0.25. That means you must design your systems to keep the water well within the drainage layer. If the drainage layer capacity is not good enough, water will pond up and you will have submergence ratio coming close to 1. Okay? Similarly, if you look at the effect of earthquake, earthquake is a horizontal force, and if I resolve the alpha h w into its two constituents, your factor of safety will become like this. So all that you will see is alpha h is reducing the numerator and enhancing the denominator, causing the factor of safety to fall. The difference between seepage case and earthquake cases, an earthquake will last for a few seconds. So it is a dynamic phenomenon which we can do the analysis in a pseudostatic manner, but we can have the factor of safety, acceptable factor of safety, fall down to a much lower value. Seepage case does not happen in a few seconds. it may carry on for several hours. Therefore, it's a phenomenon which is more long term, and during the monsoons it may occur repeatedly. Therefore, the factor of safety which is acceptable is slightly higher. There's also the third formula here, which is when I put a reinforcing element in the system. And I have put two formulae, a little complicated, plus T. So just let's look at the stability without T. That's the stability without T, right? Now what happens when I have a reinforcing element? The reinforcing element will have a capacity to take tension, right? And this is acting in which direction? Is it acting in the direction of the driving force or the resisting force? Right. Now the question is, there are two approaches to evaluating the factor of safety. One approach is that my resisting force has gone up. That's my factor of safety. And that's the top formula which is shown in the slide. The other approach is what it says is that the tensile force has reduced my driving force. So it's the way that you define your factor of safety that's important. And unfortunately, both these formulae have been used in literature. So I'm just putting both of them on here for you, that both these formulae have been used. You can use either. As an individual, I prefer to use the top formula. Why? Why do I prefer to use top formula? If my T becomes equal to W sine beta, theoretically I can have a reinforcement with very high T. So if my T becomes equal to W sine beta, what happens to D minus T? Becomes 0, F becomes infinity. So that's a kind of an enlarged or an expanded or an enhanced value of having an infinitely stable slope. So I prefer to use this formula instead, where it will not go to infinity. But both exist, and let me see if I can show you. The one approach is called the enhanced resisting force approach, and the other is called the reduced driving force approach. This formula is the same as the previous page, only there's a term for C, please remember here. And you do recall that we have said that for residual case, C will be 0, C alpha is 0. So you can remove this, but this is the general equation, because the resisting force is C plus n tan delta. So here you are getting a C term which you can avoid, but this is called the ERF approach, and this is called the reduced. And I am suggesting that you use this approach. Okay? There's one more thing we have neglected. Is this an infinite slope? R covers infinite slopes. Okay, let me understand what you know about infinite slopes. It's again very important. You've been taught infinite slope analysis in your slope stability. You've done infinite slope analysis. You're doing slope stability, you've done slope stability. Are you doing a course on slope stability? Yes, very good. First answer is yes. Have you begun doing slope stability in that course? Yes. Have you done infinite slope analysis? Yes, wonderful. Now give me an example of an infinite slope in where your infinite slope analysis can be used. natural slope. So let's look at what you're saying. It all depends on the scale at which you draw it on your graph paper. I have an embankment which is 5 meters high, looks like a finite slope, and you have a natural slope which is 500 meters high. Half a kilometer, too much. Okay, 150 meter high slope, as you can sit down and see. So you're saying the 100 meters is infinite? I'm going to draw both of them on the same graph paper because I have to fit it on one page. Will both of them look the same or will they look different? No. Both look finite to me. Scale is different. Agreed. Agreed. If I use the same scale, it will be higher. But I'm going to do circular slip surface analysis to begin with. Just let's assume that I'm going to use. Then my circle will go like this, and my circle will go like this. So what's infinite about the slope? Very critical. What makes a natural slope infinite? You are right. Some of the natural slopes are infinite. But what makes it infinite? What depth? There is no wedge here. This is a circular failure surface. You are saying if the wedge depth is to be considered. You are almost there, but there is no wedge in this analysis.
If we consider it as finite, then there is already some weight which is supporting it. It cannot have circular surface because then there would be the slope below it will be supporting it. So it has to have a surface which is parallel to the.
So height, surface which has to be parallel. We are getting somewhere. But let me again ask you this. I have a slope which looks like this. Okay? My failure surface is this. Is this a finite slope or an infinite slope? I want you to focus on this. As far as this failure surface is concerned, these don't exist. As far as the failure surface is concerned, it didn't see the ends. If I have a slope like this and my failure surface is like this, then it sees this end and it sees this end. Let me articulate my thought. I have a long slope. This is one. This is another. The failure surface doesn't see the top and the bottom of the slope. It just sees a single line. Is it an infinite slope or a finite slope? Infinite slope. Okay. So let me now bring this together. When the thickness of the failure zone is much, much smaller than the height of the slope, then it's an infinite slope. I will restate this. The thickness of the failure zone, if this is the thickness, is much smaller than this. Then it will work like an infinite slope because the edges will not be seen. Otherwise, this failure surface is seeing this and it is seeing this. It's going to be a finite slope even if it is 150 meters high. So why is it that natural slopes become infinite and man-made slopes don't become infinite so easily? I'll come back to this natural slope, and we are doing a landslide problem. So we talked about 150 meter high. What makes this slope infinite is the fact that the thickness of the soil is very less. After that there is rock. So therefore your soil is like this. That means what? That means this failure surface is not relevant because it's going to go through rock. Failure will not occur through this. Failure will occur through, and this thickness is very small in comparison to the height. Therefore, we come back to what you said. that if there is some failure along which the slippage may occur or which is restraining the circle from going down. So infinite slopes are there in nature because there's rock at the bottom, you can't go very deep. If you go very deep, you can become a finite slope. The thickness of the failure surface. So therefore, when you do infinite slope analysis, you are always presuming failure surface parallel to the outer slope, and this thickness is very small. So you'll say, sir, where is the failure surface parallel to the outer slope? It's a circular slip surface. I keep on increasing my radius of the circle. What happens? It will keep on becoming, and I make my radius infinite. Is a circle of an infinite radius a straight line? As far as this is concerned. So in your softwares, what will happen, unless they have a boundary condition that you can't take you'll find that for infinite slopes, your circles will become very flat. They'll become almost parallel to the outer slope. So we are using the same principle in the cover. Why? Because the cover thickness is, how much is the soil thickness on top of the geomembrane? Both are wrong. There's a topsoil plus the drainage layer. How much is the thickness? It's not 45, it's not 60. Drainage layer is 30 centimeters or how much? And topsoil is how much? 6. Please go and look at the covers which I have taught you. But typically the total values will be in the range of 60 to 1 meter. It may be 60 plus 30, which is 90, or it may be 45 plus 15, it may be 60. Right, and what is the height of the slope? That was the question which I was going to come to. For the cover slope to be declared infinite, the thickness of the slope is 1 meter. Agreed? What is the height of the cover slope? What is the height of my landfill? Pardon? No, I said from visual aesthetics, we don't want it to be higher than 15 meter. We can be as high as 30 to 50 meters, yes. But if you are a designer and if you go and tell your client, I'll make a 30 meter high landfill, you've begun the wrong way because you have made it higher than the 4-storied structures around you. And you don't want a landfill to rise above the skyline. You can make it, they don't have land, they say, oh no, we have prepared for this, fine. But let us say height of the landfill is 15 to 20 meters, 18 meters is what I take. So this is my landfill. And this is my 1 meter. Oh, this is looking too much. Is this an infinite slope? Agreed? It's an infinite slope. Why? There is a little wedge at the end. Is there a wedge at the end which is resisting this soil? Yes, there's a little triangle. But what is its contribution to this? Nothing. This whole weight is coming down. In the toe, there is a little bit of triangular weight saying, I'm the passive wedge, I'm the passive wedge. Yes, you are the passive wedge, but you're too small to make a difference to me. Agree? When does the passive wedge become significant and it adds? Will the passive wedge give you better factor of safety or less factor of safety? Infinite slope assumes this is not there, this slope is just going down. The moment you have a passive wedge, it gives you some enhanced factor of safety. When does it become important? It becomes important when the slope length is not that long. It is still long, but not that long. You will never find a slope of an 18 meter high embankment like, suppose it is 3:1, this is 50 meters. There will be no continuous slope of 50 meter length in any landfill. Why? I've already told you this. You basically need berms primarily to break the speed of the water of the surface runoff. And then we use those berms also for making pathways for maintenance. So when you will have a landfill of this type, your natural thing will be, sorry, I'll redo this. At every 6 meters there should be one. So there will be 3 berms. Now this gets interesting. So this is 6 meters high now. Okay. Typically, if you go read the railway manual for railway embankments or any other manuals, they'll say, please put a berm every 6 meters. You don't need it from slope stability point of view. You need it from erosion control point of view, that when the water falls down, the gully formation doesn't take place and it breaks the speed of the water. And now, if you see this, my What is my h? H is 1 meter or thickness is 1 meter. What is the height? 6 meters. Now that is not so infinite. It can be infinite, but it is not so infinite. So if I look at now the passive edge here, this passive edge is not that small in comparison to that slope. So the closer the berms, the more the importance of the passive edge. So we are not doing those formulae here, but this is a two-edge analysis. Can you see on the here that we are now looking at this problem as a two-edge problem? This is the passive edge, this is the active edge. We are assuming that there is a tension crack at the top. Normally the effect of the passive edge will be very small. But suppose you say, no, I'll make a berm at every 5 meters. Somebody goes on and say, no, I'll make a berm at every 4 meters. Slope is becoming progressively flatter because you are giving a berm. However, then you better start calculating your factor of safety, taking this passive resistance in your design. We are not doing it in this course. There are formulae which are available. You can read up Koerner, Quyan and Koerner, and you can look at the formulae, the influence of passive edge. The passive edge has almost no influence once the berms are at 10 meter spacing, because the h is only 1 meter. So I'm going to come back to this analysis. If I look at these diagrams, I do not know whether how clear they are, but we are looking at the cover and we are looking at the liner, and I've already said first we look at the soil sliding over the geomembrane, okay? And very simple, soil sliding over the geomembrane is the tan of delta of the soil on top of the geomembrane. Now I'm not having a geotextile protector, okay? Then I'll have the sand directly on the geomembrane. So above the geomembrane, we have said here that it will be tan delta 1. Delta 1 is the sand to geomembrane interface angle. Below the geomembrane, it will be tan delta 2. So there will be two different factors of safety, and if there is difference, if this is less than 1, then you will have to take out the tension. So let me give you a problem, and you'll have to take out your calculators for this if you have. If you don't, we'll try and work something out. But let's look at this problem. What does the problem say? You have a 20 meter long slope, 20 meter long slope, and that's your geomembrane. On top of the geomembrane is the drainage layer, okay? And the sand to geomembrane delta angle is 26 degrees, and the geomembrane to clay delta angle is 15 degrees. So first I want you to find out the factor of safety for the sand to geomembrane interface. Can you please do that for me? The slope is given as 3:1. And sand to clay is tan 26 degrees. What is tan beta? What is beta in this case? 1:3 is given. So can you give me inverse of 1:3? 3:1 is beta equal to 18.4 degrees. So can you give me what is this value? Pardon? 1.46. Is this acceptable? What is the acceptable factor of safety for? 1.5. It's almost 1.5. So we can, for the purpose of this class, say this is acceptable. Now what I want to know is it going to slip below the geomembrane? This is sand wanting to go down. It won't go down. It's more than 1. But will it go down below the geomembrane? Then what is the tan? Tan delta geomembrane to clay. What is the value? Tan 15 by quite clearly this is less than 1. Quite clearly this whole soil mass is therefore with the geomembrane wanting to come down. It's going to slip. And remember, you have a very gentle slope of 3:1. Now can you hold this from happening? Can the geomembrane hold this from happening? Well, if the geomembrane is anchored at the top in an anchor trench, okay? It is buried in an anchor trench which is holding the geomembrane. We'll come to the design of the anchor trench later. But if the geomembrane is anchored at the top, it can take a T. Agreed? And what is the T that you need? Please look at this formula. Weight of soil plus weight of geomembrane sine beta minus weight of soil plus weight of geomembrane cos beta tan delta. Right? This is very simple. It is the driving force minus the resisting force. So W becomes important suddenly. The more the W, the more the T that you need. So luckily for us, in this problem, classroom problem, W is given to us. W is topsoil plus drainage layer plus geomembrane. It is 310 kilonewtons per meter. Okay? So can you go back to this formula? 310 sine beta minus 310 cos beta tan 15 degrees. Please give me the value of T. Sorry, that's not right. Sine beta. Can you give me what is this value? What is the first value? 310 sine 18.43? 90? 98? And what is the second value? (310) into cos 18.43 into tan 15 minus 78.8, which makes it 19.2 kilonewton per meter. Right? And let's see what is the strength of the geomembrane. T allowable is 20 kilonewton per meter. So will the geomembrane hold this? Just about. Just about. You want a factor of safety in your geomembrane tensile capacity, you will have to put it. But at the moment, it says that it will just hold. And you can calculate the factor of safety with the T now. In our formula, there was no T. In this formula, there was no T, right? But in this formula with T, there is a T. You can now add the T and see what factor of safety you get. You can do this at home, and you have to reach the acceptable value that you want. So with this, I'd like to close that this is just one of the cases. What we have done just now is without seepage and without earthquake. But I have shown to you the interplay. If I reduce W, what will happen? That 19.8 will become lesser, because it's all coming from the weight. So there's a tendency to reduce the thickness of the layers so that the T can be lower. Here is an example of what you have to do when there's a vehicle braking force. When this vehicle is going down the slope, it will give you a vehicle braking force B. And the equations are the same, but you'll have to tackle vehicle on a ramp. So there are 5-6 cases now that you have dry slope, with rainfall, with earthquake, with vehicle, and all of them have to be stable for the purpose of stability analysis. So what causes instability? High inclination, large thickness, large weight dumped, vehicle braking force, seepage forces, and earthquake forces. And we have to do all these analysis for the making the slope stable. And let me tell you, there are a lot of slope failures in covers in landfills. So you have to be very careful about it. So we'll stop here. We've just opened our eyes to how the low delta can cause instability even in a 3:1 slope. And in the next lecture, I'll take up a couple of case studies to show you how this really comes into play in real life problems. Okay? Thank you.